I'm Ethan Kwan, and today I'm going to be showing you about, be telling you about different types of radiation. Well, first of all, thank you, all of you, for 100 subscribers. I am going to make a video on that pretty soon, so be updated on that. So, well, anyway, I'm happy. So, I am going to show you different types of radiation first, and then I'll show you my intro video later, like in a different video. I mean, thank you video. Okay, so I'm going to talk about radiation and different types of radiation. So, from an atom. So, here's an atom. Some of these are protons and some of them are neutrons, right? Like this. And this is an atom. Okay, so usually it's pretty stable and it won't decay into other things. But in some cases, it will. Like, for example, the most famous example would be uranium-238. This would be 92. So that's the most famous example. So what happens when it happens with radiation? Well, there are three types of radiation. Okay, so there are three types of radiation: alpha, beta, and gamma. The most least powerful one is alpha decay. That looks like a fish. Alpha decay. So let's take again the most famous example. What was it? Uranium-238. So you'd write it U with 238 with, that's the mass, and the atomic number is 92. So a uranium atom would look. So this is a uranium atom, U, and so to calculate the decay, alpha decay, it will go through alpha decay. So it would release alpha decay is, you're literally looking at a helium atom without the electrons, without the tiny little, it would look something like this, but whatever, that's not the point of this video. No, wait, not the outer shell. No, it would look something like this. So let me just get rid of a lot of this stuff. So this would release a lot of energy plus alpha, which is basically helium atom. So a helium atom, the structure would be, well, you put the mass up here, 4, and then you'd actually literally write He, and then you'd put 2 down here. Got it? So you would release a helium atom, but without the electrons, plus, well, you would first, to get the result, you would subtract 238 from 4, or no, other way around. Yeah, and then subtract 92 from 2. So, no, wait, other way around again. Subtract 2 from 92 and subtract 4 from 238. So first, 234. That would be 234. Oops, not 334. That sounds like a time. It's close to 334 right now. 322. Yeah, close. Anyway, so 238 minus 4 would be 234. Oops, too big. 234. And 92 minus 2 is 90. Okay, so if you looked at a periodic table for this element with 90 protons, it would be TH, or thorium. So uranium would decay into an alpha particle and a thorium atom. it would basically a uranium atom would release a helium atom getting a thorium atom. So here's a little description of that. Oh well. So basically, here's a uranium atom, and basically it would release a bigger, more stable thorium atom. Okay, so we have uranium-238, and it would decay into a thorium atom. Now this is kind of weird. How does this happen? It's kind of weird, and you're gonna have to study some more to figure it out. Okay, so I'm gonna go into the second type of decay, which is beta decay. Beta decay. It's kind of strange. It's a capital B, kind of, but it would go down a little. So beta decay is, in fact, an electron that has been released. Okay, so we have our thorium-234 atom. Thorium-234 and 90. This was the product of our alpha decay, right? So if we have this, then we will, so we have this. Now this isn't a stable form of uranium-238. This is actually another isotope. And correct me if I'm wrong, but this is probably the isotope of thorium that decays. Let me know in the comments if I'm wrong. The comments below. Anyway, so this time it would release a beta particle. And a beta particle is basically an electron. So what it would do, and of course an electron would be, E, and it would have a zero mass. Well, it would have a tiny bit of mass, but you can just round to zero because it's so close to zero. And it would have a charge of -1, right? Okay, so if it has a charge of -1, well, I think, yeah. Okay, so it would release an electron that particle, an electron, and this is basically a beta particle, an electron, and it would also result in, it still is a 234 atom, 234, and then you would subtract 90 minus -1, but it's already negative, so you mean it says you're going to add, so 90 plus 1 is 0, no wait, what? No, 91, and it would be an atom of Pa, or protactinium. And it would release an atom of protactinium, or Pa. Protactinium would be thorium plus an electron. Thorium is an electron plus protactinium. Kind of strange, but okay. Now, here is a model of what happened. You know what, this time I'm actually going to draw what happened because it's a little bit easier for you to wrap what happened. So I'm going to just draw the nucleus. I'm going to draw 90 protons. Okay, maybe that's enough. Okay, and I'm going to draw a few neutrons. Now, if we zoom into the core, like this, this would it would decrease in the number of neutrons, but it would increase in the number of electrons, and this would just emit an electron. And now you're asking, wait, what was that electron doing in the nucleus in the first place? And because they usually stay in the shells around it, right? Shell, right? Weird. Okay, so here's the explanation. It's interesting because, well, electrons aren't supposed to stay inside the nucleus. So what happened is that a neutron, and this is a just big neutron, so I can illustrate my point, spontaneously turned into a proton. But this shouldn't happen, right? A neutron is negative. It is neutral, but, well, that kind of gives it away. A neutron, neutral, got it? A neutron is neutral, but with a charge, but a proton is positive. There must have been a negative charge inside there, and the only negative charged matter is an electron. So it must have emitted, while it was doing that, it must have also emitted an electron. And that's how it changes. So a proton plus an electron equals a neutron. Interesting, right? And of course this is, I guess I can draw a little circle there so that represents that it's a neutral charge. Anyway, so this is interesting because this is pretty fascinating. Anyway, so last type of decay. It's called gamma. And sorry about this little line down here. I don't know what it's for. This one down here. Oh well. Yeah, sorry. Maybe I should go down a little more. Okay, so I'm going to take an atom of technetium. It's the first radioactive element. So this TC is weight 99 and has mass 43. So that's 99 is the mass. But this time I'm going to do an excited state of 99M. And the M just represents that it's an excited, it's an atom in its excited state. Now, so technetium is an interesting atom. I'm pretty sure it's the first atom to release a gamma particle, and a gamma particle is the most interesting particle of all of them. And a gamma particle is the most interesting of all of them. So gamma you write as a kind of like that. Decay. So gamma decay is the most interesting because it's not a particle at all. It's a type of energy. So to understand what I mean, I'm just gonna, you know what? I'm just gonna select. How do you do that? Yep, there it is. The tool for selecting. That, copy and paste and delete. Take that and move here. Okay. Anyway, so 99M, right? Oops, wrong tool still. 99M, right? So so a gamma particle, here's how it's written. So a gamma particle isn't a particle at all. Whoops, wait, why am I on lens? Oh, no, okay, I'm fine. So gamma particle looks like that. And gamma decay would be a gamma symbol with a zero mass and zero mass and zero. So it's nothing. It's just a particle of, like, think of it as light, but it's not a light. It's not light. It is light. It's like zero, but like whatever. A light particle has no mass and no protons or neutrons. So that's why it's 0, 0. So this will spontaneously turn into a, not spontaneously, but a gamma particle with 0, 0, plus, and of course we know that this is an excited state, so 99 minus 0 is 99. Oops, too big. Is 99, and it is 43 minus 0 is still 43, but it's not an excited atom anymore, so I wouldn't write an M there. But it's still technetium, whatever you call it. Yeah. Anyway, so we have three types of particles. Alpha, so alpha would look like a fish. Beta, which looks like a capital B, and gamma, which it looks like someone holding a fish by the tail, are the three main types of decay. So now I want to talk about exponential decay. So what is exponential decay? Well, actually, if the video's too long, I'm gonna cut it right here. So yeah.